Perfect. Glad to hear it. Hey, so welcome to week 3 of PLC programming. This week, we're going to learn what is a false to true transition. This is an important concept to understand for a lot of the more advanced and even some of the fairly basic functions inside of a PLC. Where to find T on, T off, and counter instructions. So those are timers, timer on, timer off, and counters. How timers function, how on timers function, how off timers function, the data array, the data type that are used for these timers and counters, how counters function. Has anybody who's seen PLCs before or even other programming, have you dealt with timers and counters? Yeah. All right, Scott. Yeah, it's one of the most, I'm not going to say most basic, but one of the timers are very fundamental for working with PLCs, because you don't always want something to happen immediately. Sometimes you want to delay, whether that's you want something to not turn on immediately, wait a few seconds. Those are called debounce timers. Sometimes you want to latch, like hold timers. And I'm sure a lot of the electricians, you've wired up physical timing relays a number of times. The process, the logic behind them is very similar. So in a nutshell, false to true transitions is sometimes called a rising edge, but it's the transition from a bit going from false to true. So when something turns on from off, or if it's normally closed, when it turns off from on, it's when the test bit, like you can see in this graphic, becomes true. That rising edge is what would then allow the counter to start to execute. So when we're dealing with functions, a lot of them, nothing will happen until, especially for the counters, until they are activated, and potentially could only activate once. So when a test bit turns on and stays on, the timer won't just keep accumulating. It has to cycle on, or sorry, this is a counter. It will have to cycle on, off, and on again before it will accumulate another count. So the input side for this counter, on the left, so when dealing with ladder logic, the inputs for all functions are coming from the left. The output side, the instruction on the rung will align to the right. So you may have noticed that when you put in your OTE instructions, they will want to kind of snap to the far right when you put them on your rungs. That's because just like when you're reading, the way you would read an electrical drawing would be the power, the line side would travel from left to right. The logic and the state of the rung will travel from left to right. So the state, what is the state of the rung when the input instruction is de-energized? So the state of this rung, the state is false. What is the state of the rung when the input becomes energized? So that would then be true. So when it moves from false to true, you can see here where it goes test bit is false and true on that rising edge on that transition. That's when the counter counts. So the counter accumulator went up to 1 from 0 on a rising edge. Any questions? We're going to kind of cover this a couple of times with the different instructions today.
Hey Ryan, sorry,
Hey.
quick question.
Shoot.
So this counter, so once the test bit is energized, the accumulate still should go all the way up to 16. So then we get the C counter up energized, right?
Yes, but for it to accumulate more, test bit would then have to transition to false and then true 15 more times. So then what would happen with the counter is when the test bit goes back to false, accumulation will stay at 1. When it becomes true again, accumulation will go to 2. Preset here is the number of counts you want before the done bit is activated. So this could be counting if you had a parts counter where every time 10 parts pass a particular sensor, you then want to freeze the line so that a new box can be put in the way. This could count up to 16, and then the done bit you could use the done bit, which is a bool, is a bit of information, could then be used to trigger further logic. So you're right, but in this state of just evaluating false to true transitions, it's only going to accumulate once. And when this stays high, it won't keep accumulating if this is just on. It has to cycle. Does that make sense?
Yeah. So then during this time, during this count up time, the CU part of that is energized, and once it becomes 16, it flips, and then done gets energized, and CU just turns off.
CU just stands for count up. So whenever the input becomes true, this function will count up. So the accumulation will move up 1 decimal, 1 whole integer, 1 whole number. And once that number reaches 16, the done bit will then transition from false to true. And then this will continue to accumulate. So just because this is 16 doesn't mean it'll stop accumulating. You can accumulate 10,000 in here if you want, but once the accumulator is greater than or equal to the preset, the done bit is true. And we'll get more into how the counters work. The concept we want to understand first is transitioning from false to true. So a false to true transition. Sorry, coworker following up. Okay. A false to true transition describes a rung that goes from a de-energized state to an energized state. For example, our test bit we just saw. So when the test bit is off or false, then the output, which in this case is the counter, is false. When the test bit becomes true or is turned on, then the output is turned. Then the counter will accumulate, but the transition with the output would turn on. So if this output were actually one of the OTEs from last week, it would just then turn from false to true instead of performing a function. So most instructions perform their intended action every scan cycle when their rung is true. However, some instructions perform their intended action only on a false to true transition. So That means if you're doing, if you had a move instruction where if test bit were true, move a value into another value, every single scan cycle, the move would execute every scan. Or if you're doing an add or subtract or compute, they would execute every scan. But there are some instructions that are tended to only work on these rising edges or transition from true to false or false to true. Those instructions, even if the rung stays true after the instruction is performed, the instruction will not trigger a second time until it can see the rung go from false to true again. So does that make sense? Any more questions? I know I just repeated myself a bunch, but it's kind of a a Zoom link is not easy to find these days. Did it not work right from the D2L homepage? Okay, I'll write a note down and I'll double check that that's configured properly. Did anybody else have issues using the link? Okay. Needs to be on the weekly tab. Okay, after the lecture, I'll take a look at that. So, data storage. So last week we talked about various data types. There are some common ones. So we have bool, integer, unsigned integer, double integer, unsigned double integer. So these are kind of the base building blocks of data manipulation. There's also reals or floats, depending on what they're called in the different platforms that you're using. But these are the building blocks of a lot of things. All binary instructions are essentially, or Boolean instructions, discrete instructions and logic are built on the bool or individual bits of integers. And up until I couldn't tell you when, but there was a time where you only had integers to deal with. You didn't have real values processors. Some of those old 8-bit processors, you only had integers. So if you needed to do anything with decimal places, you had to mess around with some funny math in your HMI software. So PLCs couldn't do fractions, part numbers, only whole numbers. PLC manufacturers stood to benefit from including more complex data types that contain a combination of data types. So this means that there are data types that are designed for more complex actions than just examining if something's on, examining if something's off. So for example, a timer, the function itself has an enable, which is a bool, a timer timing bit, TT, which is a bool, and a done bit, which is also a bool. It has a preset, which is the setting for how long you want the timer to accumulate for, and that is a double integer, and it has an accumulated time, which is also a double integer. So the timer data type is used for both timer on and timer off timers. And there's some other types of timers in there, retentive on timers as well. Both timers use what they need from the timer data type. So this concept of data types is common for all manufacturers of PLCs. And even if you look at the SLICs, the SLIC 505s and the MicroLogics, they do have timer data types in their data tables built in, and they also have description, enable, done, timer timing, preset, and accumulation data locations inside those files, because timers and counters are, again, the very part of the very basic building blocks of being able to execute and perform logic. Does this make sense? Like the data type for a timer contains more than only one type of data. So last week we were talking about bool data types and integers, and how integers can be either whole numbers or individual bits. Now, timers can be bools and dints. Any questions? Okay, perfect. And then I'll show you how we can view this information once we get a little to the demonstration side. So timers. So timer on is the T-on instruction, is a non-retentive timer that accumulates time when the instruction is enabled and the wrong condition is true. So that means that a T-on timer will accumulate time for as long as its wrong is true. So whatever condition comes from into the input, as long as that is true, the timer will accumulate time. So the accumulation will go up. If there is a timer timing bit programmed somewhere, it will be true while the accumulator is running. And once the accumulator reaches the preset, the done bit will become true. So unlike the example of the counter, which only executes on a rising edge once, the timer will run continuously. So to add T-on into your program, you would just edit a rung. You can either type in T-O-N, you can see up here, into that text editor, or if you pull down, if you're working in your palette, you can bring down a T-on. So edit your rung, type in T-on, it'll show up. You could also add it from the palette at the top. Preferred rung again, look at the instruction bar. Yep. Sorry, your timer, click on T-on, and it'll snap into the output. You could also drag it down from the palette. We'll get to do that later. So this is an example of a T-on, a little blurry. So whenever the rung is true, the T-on will begin timing when the rung is active. So why is it? When it's done, the output becomes active. So the done output will become active. So like I was saying, when the rung is true, the timer becomes enabled. The accumulator will accumulate time until the preset. And once the accumulator reaches the preset, the done bit becomes true. For Logix 5000, the preset is entered in milliseconds. So if you're asked to do something in seconds, you have to enter in 5,000 for 5 seconds. This is a departure from some other platforms you may have seen where you can change the time scale, where you can say, I want it to be 1 second, 1/10 of a second, thousandths of a second. These timers only run in milliseconds. So sometimes if you want to enter in set points, or if you're interfacing with like an HMI and you want somebody wants to enter in 5 minutes, you may have to do some math to convert 5 minutes into 600,000 milliseconds. 600,000? 300,000. Yeah, sorry, I went 2. So remember, the preset is in milliseconds. So for 8 seconds, we would enter in 8,000. Any questions? So what does the T-on do when the input is active? In this example, we're using a T-on timer with a preset of 2,000, so 2 seconds. So if you look at this chart, you can see here where 0 is no output. Sorry, 0 is no output. Sorry, input, and then the done bit. So this would be your output. 0 is false, 1 is true, and the done bit is false, and the done bit is true, graphed against time. So when the input is false, the output is also false. Then at 2 seconds here, we can see that the input is a rising edge, or transitions from false to true. And then the done bit remains false. So then 2 seconds later, or 2,000 milliseconds later, the input is still on. After 2 seconds, the timer done bit will then transition to on. So the T-on timer times for X seconds, in this case 2, and when it is done timing, the done bit becomes active. So for the T-on, the non-retentive time, if at any time the input becomes inactive, the done bit also becomes inactive. So once it's done, so if this input stays on and then cycles off, at the same time the input cycles off, once the done bit's done, the done bit will also deactivate. Does that make sense? So what do you think would happen if at 3 seconds the input dropped off? Anybody have a guess? No? All right. If the input does not stay true for the entire duration of, sorry, I hit the microphone, for the entire duration of the preset, then the preset will reset. So if it dropped down at 3 seconds and came back on at 4 seconds, then it would wait until 6 seconds before the done bit, or the done bit will become true. So on timers, most people get on timers right away. Off timers, they are a little tricky. So the T off instruction or off timer instruction is a non-retentive timer that turns an output done when the rung is true. Then it keeps the done bit active for the amount of time for an amount of time after the input de-energizes. So double click your so this is adding in a T off timer. So again, when you're online with your processor, you would double click on your rung. Then you could type in T off timer here. It would add in a T off timer. Notice it looks the same as the T on timer, with the exception it says TOF. The description is in here as well. So if you're not paying attention when you're reading another piece of code and you don't see that it's a T off timer, it can really mess you up. I've had T off timers catch me in somebody else's logic just because I assumed it was a T on timer. T off timers aren't used as often. So again, a T off timer here. You can see that it has a done bit. So the T off timer's done bit is active when the instruction is true. The T off timer begins timing once the rung is inactive. So that means on the trailing edge, or when it cycles, when it moves from true to false, that's when the T off begins accumulating. Then the timer's done bit is held active for the duration of the preset until it has accumulated, and then the output will turn off. So if you wanted this, if you wanted the preset, if you wanted this to run for 4 seconds, what would you need to type into the preset? That's right, 4,000 milliseconds. So what does a T off do when input is active? So for this example of the T off timer with a preset of 2 seconds, so it's the same duration as the last one. Wait for this fancy animation. So the same time graph. So you'll see this in a lot of examples when you look for how certain functions run. This time graph as to what they'll do is a very common way for that what they do is expressed. If that makes sense. And I'm sure any electricians who's actually used timers, like installed timers, you've looked through the microscopic manuals and seen something similar to this, but instead of output, they'll say coil, or input will be coil, and this will be like relay 1, relay 2, but it's all against time. This, yeah. Anyway, so for the T off, when the initial input is false, the initial output state is also false. When the input transitions from false to true, the output immediately transitions from false to true. After 2 seconds, the input becomes inactive. Does anybody guess what the output will do? If you guessed it would stay on for 2 seconds after, you are right. So once your input becomes false, only then does the timer start accumulating. And then once the timer has completed, then the output of the timer becomes false. So again, for the 2 seconds, the output will stay on. Yeah, so this is used for sometimes if you have push buttons that you want to hold. As soon as you press the button, you want something to happen immediately, but you also want to give some time once the button's been released before a cylinder backs off. Let's say there's a multi-stage for disabling a piece of equipment. You can press a single button, immediately fire your timer, and on release of the button, you can set your off timer to give enough time for a piece of equipment to move before the cylinder is retracted or extended. Yeah. Any questions? So it is also important to note here that when using a T-off timer, even if you cycle true for a single scan, the timer will still execute. So it's just something to keep in mind. The output will be on for a minimum of whatever your preset is, no matter how long your input is active. So this is the visualization again for 2 seconds. I don't know why this is repeated. Let's do it. The input is 0 and the output is 0. Once the input cycles or transitions from false to true, and the output will then transition from false to true. So on a leading edge, the T-off timer immediately turns on. Should the input cycle repeatedly and then hold steady state for a little longer, well, the output will just stay on the whole time. And then at the last trailing edge, it will then stay on for the duration of the preset. Does that make sense? Are there any questions? All right. So counters. Counters instructions are useful to keep track of how many times a variable, a condition has become active. So in Studio 5000, CTU is an instruction that counts upwards. On a false to true transition, the CTU instruction will count up by 1. When the accumulated value is equal to or greater than the preset value, the done bit will then transition to active. So what does the counter do when the input goes true to false? Why is that T off there? Ignore that T off. The CTU with a preset of 3 So when the input cycles once on the first rising edge and then drop, the counter will accumulate 1. On the second rising edge, the counter will accumulate to 2. So it will accumulate 1, but it will add. So it'll go to 2. And then on the third one, the accumulator will complete. So the accumulator reaches 3. So for a preset of 3, that means that the done bit will turn on once the accumulator reaches the preset. Does that make sense? Any questions on counters? Yeah. So the false to true transition, or leading edge, is the input side of a run going from false to true or 0 to 1. And this doesn't necessarily mean it has to be a single bit. This could also be from evaluations. So if you're looking to see if there's a value greater than a specific set point, when that happens, that evaluation is outputting a bool, is outputting a individual condition. So it's not just for limit switches, these can be conditions greater than, less than, equal to. So you can evaluate conditions in the field to trigger these counters, to trigger these timers to do something. So whether it be a level reaches something too high, if it's above a certain threshold, then it could trigger the timer. If it's above that threshold for 5 minutes, maybe you want to start a pump. Maybe if the level gets too low, you want to start a pump to fill that tank. So you can evaluate live conditions of a system, add in delay timers to then act on those conditions. Maybe it's not beneficial to, the moment the sensor sees something, to immediately turn on a pump and then immediately turn it off. Maybe you want to make sure that the switch hasn't seen, there isn't a false signal. You want that switch to be latched in for a number of seconds, then turn on a pump. Anyway, so there's lots of things that can be a true to false transition. There are many unique data types. So today we added to our repertoire here timers and counters. So timers and counters are data types that include other data types inside of them. So they're built of other building block data types. So bools, which are encapsulated as done, enables, and timer timing bits, as well as the period that they're on. So we have the set point, the preset, and the accumulator. So T-on timers, they'll receive their input, then they will wait for a period of time before turning on their output. T-off timers will immediately turn on their output when they receive their input, and they will keep it on for a duration after the input goes false. And then counters, they operate on a false to true transition. So they will only accumulate on a rising edge. And that's the presentation. Right. So To prevent me from being locked out, I connected in before, and I've already transferred on the applications for the lab. So the lab this week is for timers and counters. So I'm not going to go through the specifics of the lab, but I am going to demonstrate how some of these functions, these timers and counters work. A couple of things you may encounter, how to enter them in, how to look at their data as well, before letting you guys loose on your labs. One thing, so I saw your labs from last week, and these, the instructions in here say to call it QB Electrical Week. QB is just the initials of the person who developed the lab, Quentin Bonnet. When you do yours, you can add your own initials in and call it the PLC programming course or CNTR1351. I thought it funny that most people sent in Quentin Bonnet initials. I have not dogging marks for that. There's just something I noticed. So again, when you bring your files in, you'll need to extract your HMI application by using the Factory Talk ME interface application manager. We'll call this one Ryan. That's invalid because it doesn't like special characters. Download to my emulate. Download. So one of the things that I was playing with last week was trying to see if there's a better fix than restarting the computer for when you try to launch your emulator and it tells you somebody else is already using it. So unfortunately, you can't send a Control-Alt-Delete to these machines. At least I haven't figured out how to. So launching a task manager inside from the Windows menu, you go to this MU Logix. If it's already running and you haven't launched it, end that task and then try to open it. I had success with that twice. And then another time I had to dig through the actual services and shut down an RS Link service. So try to shut down the MU Logix in the task manager before restarting the whole computer or trying to jump around to different machines. It might save you a lot of time. Mine's working, so I'm not going to do that. I didn't know I could move that. And now it's in an annoying spot. Jeez. That was and then once your, I'll do it this way. Once your Factory Talk application has extracted, go to Factory Talk View, Factory Talk View Studio, Machine Edition. Yes. and wait for it to load. So once we're in here, we can either go to application, go test application, or just hit this running man here, and it'll create a local simulation runtime file for you. And I would go here to remote audio and click mute, because I find it incredibly irritating that every time you click a button in this software, it chimes at me. There. So just that chime, I don't like it. It's annoying. So we turn it off, and it doesn't happen anymore. If you're curious, every one of those instances of the audio is in every item. So to get rid of that, and I looked at it, you would have to go through every single icon and delete that, just uncheck that. And it's just, it's not worth it. It's not worth it. All right. All right, so in the environment here, let's get some. So you can see, you can click, if you just click up here on the different items, they'll drop in, and you can move them around. You can play around with a bunch of different ways. Once you've worked on a bunch, you might find you prefer entering things in a specific way. So I'm just entering in some test bits. Now test bits doesn't exist. So, but because I know that I can create a int, I can't type, but I can create a dint, and then I can reference specifically the individual bits of that dint. I can type those in, and then once I create the test bits data type tag in the controller tags, it will automatically fill in. Right. Ah, there we go. That's why it didn't work. I created those in the main program. But it'll automatically create the data type here, and it'll fill in. You can see that the description came in. So again, for timer, so we can create time on timer. Right click, add a new one. We'll call it time. So it is a data type of a timer. So this is by default wanting to put it in program scope. So I actually prefer to put everything into my controller scope, and I'll click create. So you'll see that once the data type is actually created, that's the only time. That's when the preset and the accumulator will show up. So right now, even if I T off, it doesn't know what it is because it hasn't been created yet. But I've called it T off timer. We can go here into our controller tags, and this is another way to add tags. So we called it T off timer. It is a data type here of a timer. Once I click off, that is created. And if I spelled it right, now our T off timer is valid. We can now assemble these rungs. And we'll see that these presets aren't set. So we could set this one for 10 seconds. So remembering that this is milliseconds, 10 seconds is 10,000. We can go back into controller tags and we can expand these data types. So when we expand the tags here, remember how we were talking about, we've got the bool data types. So up here we've got real, a float, style, dint for the encoder position, these single integers, double integers. Those are just the bits of the double integer. When we start adding in here the T on the timer data type, it has a bunch of other information inside of it. So it's got the timer on dot done, which is a bool, the timer on dot TT, which is a timer timing bit, which is a bool, its enable bit, which is a bool, and then it's preset and accumulator, which are both double integers. Same thing with the T off timer. So you can come here and we can even set the preset to 2 seconds from the controller tags under monitor. And when we go back, it's changed. So when you're online, you can access this information in whether it's live in the code or in your controller tags. If you've decided to monitor things, monitor. So monitor will bring you here to the controller tags as well. So instead of having to go open up controller tags all the time, you can click on your tag and go monitor T off timer, and that'll bring you to its definition location. Any questions? I know I'm going quick here. I don't want to leave anybody behind. And this is a lot of what's in the lab. I'm just not going through it step by step. So with your T on timer, we can turn it on all we want. You can see here, but it'll reach its 10,000. I have 10 seconds in there. 10 seconds is a longer time than you realize until you're waiting for a timer to go. So it counted up, and once it hit 10 seconds, plus a very small amount of time, we're talking 18 milliseconds, it's done. The timer froze. It's not that it froze, it's just it's not accumulating anymore, but the done bit turned on. So you can see here that it's visually telling you that it's enabled and it's done. And if we wanted to access that done bit, we could, let's do it in this rung. So we'll do the favorites, that, and this. So you can access the done bit here. And now when I assemble these, we have the T on is done. So when this bit is on and stays on, once this done bit completes, it turns on the T on is done. So this could be a pump start. This could be any tag really. We'll turn that off. So what I'm hitting there is Control T on my screen, but that is toggle bit. So, excuse me. If there's a bit in your code, as long as it's not being controlled elsewhere, meaning as long as it isn't an output, I can't toggle this bit on because the code is actually executing and turning it off. Because this rung is false, I can't force that on unless I turn on actual controller forces. So, but because this rung I just created, there's nothing writing to that, I can toggle this on in the code whenever I want. After 10 seconds, 10 seconds is too much. Let's go, but doesn't matter. You can see now the T on done didn't turn on until the timer done turned on. So let's play with that a little more. So So the timer timing bit of a timer, fairly self-explanatory. Right now, the timer done bit is on, which means that the timer is not currently timing. So when we trailing edge and come back, now what's going to happen here is the timer is going to turn on and start accumulating immediately. After 10 seconds, this T on bit will turn on. But as soon as this timer starts counting, this bit will turn on and it will stay on for 10 seconds. And once the 10 seconds is over, so the moment that this turns on, the timer off timer will activate. So it activated and turned on the T off timer done bit immediately. After 10 seconds, that timer's done, but this timer is accumulating. So it is now accumulating for 15 seconds. And once it's done, once the timer is complete, the done bit will turn off. Does that make sense to everybody? So I'm editing this wrong. So I'm going to add in. So XIC, so examine if closed, T off, timer done. And then I'm going to add in a counter. So because I typed in tofftimer.done, it filled in my examine if closed in that text editor, and then I added in a counter. So that counter, I didn't specify a tag, so I can either add the tag here, counter 1, again, scope is a counter, is the data type. We'll create it. Now you can see that the preset and the accumulator are now zeros from question marks because it's a valid data type. Let's do 5. So again, so trailing edge, this input turns off, turns back on. So now the timer runs for 10 seconds. Once it's complete, the T off is no longer has an input, but its done bit stays high. This done bit's been on since I cycled the timer, and it's only accumulated 1 in the counter. So the counter will only count on your rising edge. So if this turns off and back on, we accumulate another 1. So you can have lots of counters. I've seen counters. So if you want to use a counter to do math, I've seen counters used for volume calculation, knowing that a certain one input turning on then becomes a pulse for a tipping bucket gauge. You know, count the number of tips that you've done, and then you can perform math on these accumulators. So let's say you wanted to know if counter 1.acc was greater than 2 but less than 6. So you can do logical evaluations because the counter is 2, it's not greater than it. But now the counter is greater than 2 but less than 6. I don't know why you would want to evaluate that. It's just an example that came out of thin air. But you can evaluate it. Now, because the T off timer will run for 15 seconds no matter what, even if I toggle that bit off immediately, well, this counter didn't complete, but this timer starts. But if this input turns on again before it completes, well, it never actually completed. And the timer, the counter never accumulated. So you may have thought, well, this counter is accumulating every single time you've turned your bit on, but it doesn't. It only accumulates every time that this bit has been off for at least 15 seconds. So T-off timers can be used for occupancy sensors. So one of the most common places I've seen a T-off timer is actually used for when people use their security, their PLC system as a security system, where they'll hit an arm button or they'll hit a button to make sure something happens, but maybe they then have to move out of the way. They have to get out of the way, or they have to load a part in, and it'll wait for those 15 seconds and give them 15 seconds to do a task. And if it's not done within that task, the bit turns off and it's no longer ready to go. Does it have to be a T-off timer? No, like I said, they're confusing, and there are some tasks that require it, but most things can be done with T-on timers. But you do need to understand the difference, because the T-off timers can be confusing. Any questions with timers, counters so far? Okay, so one of the last things with counters we need to cover. So again, we can go in here and see your counter data types. So just like with the timers, there's a bunch of different pools. So we've got your accumulator, we've got count up, count down, done. I forget what OV and UV mean at the top of my head. We can look that up. I don't use them often enough to have that memorized. So anytime you need to find information about any function in Rockwell, you can look this up. So you can either click on the data type and hit F1. It's a standard Windows help key, or right click, get instruction help. And it'll tell you about the structure, all of the compatible controllers. We've got counter is a data type, that's its tag. Its preset and accumulation are dints. So count up, the count up enable bit indicates the count CTU instruction was executed. Done indicates that the ACC is greater than or equal to pre. OV is an overflow. Okay, instruction, when the counter increments past the upper limit of 2,100,000,000 and whatever, the counter then rolls over to a negative number and starts counting again. Yeah, don't let that happen. Bad coding, underflow. That's why I never see those. I've never run into a condition where I've had something happen 2 billion times. I've seen older controllers with integer limitations, and it's pretty easy if you've got like a bottling machine or any sort of parts counter that's running 24/7. You can hit 32,000 parts pretty quick. 32,000, if you remember from our data types, integers max out at 32,768 if it's signed. And if you go over that on some of those controllers, it's a major fault. Your preset is a dint, your accumulator is a dint, and that time graph that I was showing you earlier, again, you've got your example of your time graph in here showing you how your accumulator steps, your done bit, how it will step based on your input condition and your count up condition. It'll show you how you can program them in count up. So flow chart, an example for ladder logic, you can look at the countdown, which does the exact same thing. Your preset just starts up and then moves down. Or so your accumulator starts up and then moves down. So the last thing we need to cover with counters is how to reset them. So there's a couple of ways you can do it for Rockwell. There's a couple of ways to do it for Allen Bradley Rockwell. Some other controller types, there's only one way to do it. So I'm gonna show you a couple of ways here. So I'm gonna take test bit 2 and so one way to clear a counter is to move a 0 into the accumulator. You can see you can clear it even before it's done. It doesn't have to be done. I'm going to activate this rung. I'll activate it. It's written it clear. It will immediately write that in, turn it off. You've now cleared your counter. So because the counter, this is a controller tag and all of the parts of the data type are accessible, we can write into and we can look at the accumulator for these tags, for these counters. Timers as well. You could do the same thing with a timer if you wanted to. You can look at these accumulators. Let's say you had, and you may need to do this if you're working on a machine and the machine is going through, let's say you're doing food and bev, and one of the most important things for food and bev are CIP, clean in place processes, where there's rigorous and reportable times that things have to happen. So you must reach certain temperatures for a certain amount of time for disinfection to be true. So when the operators activate a CIP cycle, the HMI machine will normally give them a countdown timer. You have 10 minutes until the next step, 5 minutes. Well, normally you could take these timers, but you can't just show them 15,000 milliseconds. That doesn't mean anything to anyone. So you can actually do some math on them. So if we multiply, you gonna work for me? By 60,000, I think that'll give us minutes. I think that'll work. That should divide. So it's accumulated a quarter of a minute. So you could do the math on that to switch, whether you're going up or down. You could tell them how much time is accumulated in minutes or hours. You can do the same thing. You can show them the accumulator counters. So this works. This move to reset, that works for Rockwell. It's not my preferred way. So the other way I like, let's get a, So we've seen, and I'll show you up here a bit. It's in little bits. No, it's going to be in the count. So up here in your palette, you've got your time on, your time off. You've got a retentive timer on, count up, count down, RES. So RES is an output. It stands for reset. So we can reset counter 1. So by pulling the reset in, by activating the reset with true, it will reset the accumulator, but as you can see, it won't count up if you hold it. So the reset won't show you like an OTE will that it's on, because it's part of the structure of the function, and you can't see, you'll notice inside the counter here, you can't see a reset happening. So if you do use the reset, you kind of need to make sure that you're not holding it on all the time. You're gonna have to pulse that. So write logic where if it's done, if something happens, make sure that it's only on for a single scan, or else you could risk. Oh, it's like Janessa got disconnect. You could risk just holding your counter at 0 for forever. This reset will also work for timers. So if I were to point this at a retentive timer, so the lesson I just realized doesn't talk about retentive and what non-retentive is. So these timers are non-retentive. That means that if I turn this on and then off before it's done, it clears. So it goes back to 0. So the T on timer must complete. It's always needs to go all the way up. But if it does not reach done, it won't, like if the accumulator doesn't reach the preset, it won't hold that value. If you were to use an RTO, which is a retentive on timer, so you'll notice that nothing really changed there. The retentive on timer is the same data type. It's the same timer. It's got the same information in it. This is just what's happening in the background. So in the controller itself, and I don't think we can, no, we can't look at it. Retentive will store past accumulated values. So if I stop that, it still has an accumulation running. So if you needed something to run, if you needed to keep track of how long something had been on, and you know it cycles on and off, and every 10 seconds you need something to happen, even though it cycles on and off, you can use an RTO, a retentive on timer, to store that information. And again, with the retentive on timers, this is a good tool for capturing elapsed time for some applications. Even an even better way to do kind of elapsed time would be to use an RTO with a smaller increment. So if you wanted to elapse, say, a pump that runs for a number of hours a day, but you don't want it all stuck in a retentive on timer, you could nest some timers here. And a counter. So we can put in a counter to that's not gonna work. Bring this down to I will explain what I'm doing. So in this example, oh, let's go 100. I messed up. No, I was wrong. So my brain's not working right now, so bear with me. With this retentive on timer, yes, this is how a lot of people code. So every 6 seconds, this counter accumulates. So that means that this is a fraction of a minute. So maybe not the best example here. I was going for hourly, but you could set this for every 6 minutes. If every 6 minutes you accumulate 1/10 of an hour, and then every 10/10ths of an hour, you would get an hour. So you could actually accumulate up. This would work if my math were right. It's 360 seconds, I think. Is that what 6 minutes is? Yeah. So every 360 seconds, we accumulate 1/10 of an hour. Every 10/10ths of an hour, you accumulate an hour. So now you can look at the accumulator here and the accumulator here and know that this, even though it cycled on and off a couple of times, has run 1.0 hours, 1.5 hours, whichever, and they will reset themselves. Then one of the things you can do is add in another rung that at the end of the day, so this could be a daily runtime, at the end of a day, evaluate to reset these counters. Does that make sense? Why you might use an RTO instead of a T on in an instance like this, and where you might use a retentive on timer instead of straight T on timers. Are there any questions before I let you loose on your lab? Can anybody hear? Thank you, Saul. Just talking into a void sometimes. Talking to my 4-year-old. Sorry, no offense. You're not 4-year-olds. Yeah. So if you look at the lab, which is posted on D2L, it tells you to download our, you should be familiar with it now, the lab simulator and the visual interface. It points you in the directions of some lab tips just for getting connected into the touchscreen and the simulation mode. You should all be pros at that now. We are using the station 1 to 8, so ignore the 9 through 16. It tells you the points for the different inputs and outputs. Down here, it explains that we want to program, again, in the main routine. Don't delete the simulation logic. Just add everything. Whoa. Like I was doing right in the main routine, either above or below, but leave this rung in here. So it goes through, asks you to create some pretty specific rungs for linking them to your push buttons over here. So a start push button, your stop push button. Why are you dinging at me? PA and PB is going to turn on some part release stuff, the diverter. So the simulation logic that's in here, it does reference down further. So once you build, and then it asks you to create some timers and fill out your, what do the timers do in your different stages? Call them different things. More timers. Does the red light, does the stop button not work? Fill out your answers. And then there's a last challenge to challenge yourself if you wish. And then again, submit this either as, you know what, submit this as a as your, as it says as a report, but you can also send me your ACD file. So if I can plug it in and hit the buttons, and if the buttons do what the buttons are supposed to do, then it saves me some time, and I'll glance at your code and then submit it again here where it says name. Use your own initials if you want, or you can be Quentin. He's a lovely individual. Okay, guys, how about it? I'm gonna be floating around here. I'm gonna go use the washroom for a bit. So connect in, get started on your lab, and I'll probably be back at my desk. I'll drop a message in the chat when I'm back. Oh, someone's got a question.
Laurent.
Hi.
I joined the class a bit late. Did you talk about something on the last assignment, or what did I miss for the first 15 minutes?
Nothing really. I asked if there were questions about the last assignment. I haven't had a chance to mark them. So what I'm going to look at while you guys are working on this lab is looking at the quiz and the labs from the last one. So did you have any specific questions or concerns about the last lab? You can we can probably step aside if you wanted to, or ask them right now.
Not really. I just noticed in terms of trying to get on to the VMs, it's always busy at night or even sometimes during the day. So what I did was to probably get up early in the morning around 4 o'clock or something like that.
It's very early. Yeah, if you guys can't get in, there doesn't seem to be like there's very little allotment for us for scheduling. So the open access labs are kind of a free-for-all. I was told that they automatically spin some up. So as they're being used, they spin up additional ones. And I was told just keep refreshing the, what's that page? The page that lists them. I know that doesn't help. Course content. Where is it? Connecting in. Sorry, I'm trying to pull up the connect.
I posted a link in chat if you want to just use that.
Perfect, Vincent. Yes. Yes. So yeah. So in theory, the ones that show up on this list should be available. So if you open it and you spam F5 or refresh, you should be able to connect into these. Should. That's what IT told me. So as they get used, as they are logged into, they should remove themselves from this list. Now, I know IT people say things should work a specific way a lot, and they don't. So take that with a grain of salt, as I have. And don't go to the planetarium or Mentum Planet. I don't know what that is. Any other questions? Computer issues, unfortunately, for a remote class are going to be infinite and never ending. Yeah. If you want, I can send this to you guys, I think. Save. Sure. I think I can. I wonder where that's saved. Saved here. There it is. All right. I'll throw that up in this week's D2L somewhere. I'll add it to the lab. There, you have a copy, Saul. Yeah, so get started with your lab. All the files you need, if you need to download or whatnot, all of the files are in the tips and templates. Again, I'm gonna jump to the washroom and I'll be back in a few minutes.